Hi, everyone. Okay, so not too many participants. So today we're going to talk about geometry, and we have David Vaccaro again. So we're just waiting for him to join. Can people hear me? Okay, perfect. All right. Okay. And yes, David said that he might be a few minutes late. We'll just wait for him to join.
Hello, everybody.
Hi, David.
How is everyone this week? Right, I've just got through the door, but I'm really excited. Second week on Euclidean geometry, and I'm just going to share my screen. And as I share my screen, I'm going to tell you, oh, I need to be made haste. I'm going to tell people a little story, which is that when I was the age of...
Sorry, David, just a little heads up. The assignment hasn't been published yet, so it's going to be published tomorrow. So students haven't seen Euclidean geometry 2.
Oh, right. Okay. So shall I talk a little bit about you? I can talk a little bit more about Euclidean geometry 1.
No, we can still do. Just be aware that they haven't seen the assignment yet.
Okay, fine. I mean, we're all in the world of Euclidean geometry, so all is good. And what I really wanted to begin with actually is sort of something which is sort of in some sense between the sheets. So when I was roughly your age, I was very lucky. I was invited to a UKMT masterclass, and it was given by somebody called Dr. Christopher Bradley. And if you look at the UKMT publications, you might see lots of things which are written by him, and he was phenomenal. really got me into maths, and it was a similar scheme to this, but it was sort of transformed my life in many ways. And he was incredible at geometry. And I remember him saying, well, him just sort of, he used to set a lot of the BMO problems. And I remember him sort of saying that one of the things that is he couldn't quite understand, or well, one of the things which someone in the class said that they couldn't quite understand is, how did the Greeks come up with all these results? How do you know that the angle bisector, you know, that the angle bisectors meet in a point, or the perpendicular bisectors meet in a point? And what Christopher Bradley said was, because the ancient Greeks spent a lot of time drawing stuff. So when I go to my shared screen, I still can't share my screen. Can you make me co-host? Sorry, Vlad, can you make me co-host so I can share my screen? Sorry, I've got this webinar. Sorry, everyone, I'm not able to share my screen at the moment. I'm just. Okay, wait 1 second. I'm just gonna see if I can contact Vlad just so he can make me co-host. I'm a little bit stuck until I can share my screen. Yeah, I can answer a question about complex numbers. Oh dear. I don't know how to contact Vlad. I mean, I don't know. I don't quite know what to do if I can't share my screen.
Apologies, David. Now you're the host. Very sorry about that.
Oh, thank God! Thank God. Right, let's start, everybody. Let's share my screen. And which window do I want to share? I've got too many windows open. Okay, so I'm going to share this one. And right, so the story I was telling a little while ago was basically this question of how did the Greeks come up with all this geometry? And the answer was that they drew a lot of stuff. Okay, so, and I cannot recommend enough, both to sort of answer problems about geometry, but ultimately just to find out new facts about geometry, to actually draw things. And without doubt in my mind, although other things might be available, the best package for doing geometry is this one, which is called GeoGebra. Okay, so we go on to the geometry settings. And what I'm going to do is I'm just going to show you what's there. So there's basic settings of drawing segments and lines. And then there's more advanced settings where you can draw standard constructions, so perpendicular lines, perpendicular bisectors, angle bisectors, and so forth. And what we're going to do to begin with is I'm just going to draw a picture, and we're going to see from this picture what theorems emerge. Okay, so I'm going to draw a familiar picture. Okay, I'm going to draw a triangle. So there's my triangle. And I'm going to draw the perpendicular bisectors. So I click on perpendicular bisector and then the various points. And what happens to the perpendicular bisectors is that they meet at this point in the middle. Now, you probably think, well, you probably know what I'm going to say about this point in the middle, but put it into the chat. Can anyone tell me what's special about this point in the middle? So if I click this point in the middle, so I'm just going to create a point here. Okay, people probably know that that is the circumcenter of this triangle. Something which is worth playing around with in GeoGebra is the ability to move points. So let's say that we, and this is a familiar theorem, but let's say that we had drawn the three perpendicular bisectors and we noticed that they met in a point. Something which we can do is we can now move the points around. Now, something which is not obvious, because most textbooks show the circumcenter inside the triangle, but despite being the center of a triangle, if I move the points, the circumcenter moves on the outside. Okay. Can anyone just watch as I move the point and make a suggestion about what is different about this triangle, where the circumcenter is on the outside, compared to this triangle, where the circumcenter is on the inside? So we've got inside, it's like being at the optician, outside, inside, outside, inside, outside. What changes? Okay, excellent. There's a suggestion of acute angles. Okay, so let's try and find the edge case. So the edge case, when the circumcenter is on the edge, we get a right angled triangle. And for people who were here last week, they will recognize this as being the circle theorem or its converse. So if you've got a semicircle, then that subtends a right angle. If I move, once the circumcircle moves onto the outside, then I've got an obtuse triangle. Okay, so if you're doing a geometry sheet, any geometry sheet that you would like, then conjecture forming is best done through drawing these pictures. Okay, I'm just going to go back a little bit though, and I'm going to get rid of an object. So I'm just going to, oops, So I'm just going to select the circle, and I'm just going to get rid of that circle for the moment. Okay, so what I've got now is I've got my circumcenter, and I'm going to get some points. I'm going to get the midpoints of these three edges, E, F, and G. And I'm going to draw a triangle EFG. Now, can anybody stare at this in the chat long enough and be able to tell me anything that they notice about the, well, any result that I've just, can anybody notice any theorem that I've just proved? So this is like reverse engineering math. So this isn't solving a problem, but this is drawing a picture and then realizing what problem have we solved. So what fact about triangles that we know, but actually I don't think it was proved on sheet 1, have we just proved? Let's look into the chat. So the area of the inner triangle is 1/4 the area of the actual triangle. That's certainly true. But this point D, until very recently, we were regarding as the circumcenter of the triangle ABC. Okay. But can anybody conceive of a different way of regarding the point D? So actually, what I'm going to do now is I'm going to move to my OneNote so I can write stuff, but I will come back to this picture. So I'm going to take my snipping tool. I'm going to snip this picture. And I'm going to change my share. Where's my OneNote? And I'm going to do a new page. So this is Euclid webinar. So the point D, oops. And why is it not letting me draw? Maybe it's out of battery. Let's try this one. It's a bit thick. Okay, so the point D is the circumcenter of triangle ABC. Triangle EFG is the triangle made of the midpoints of AC, BC, and AB. What can anybody tell me about this line EF and this line AB? So EF is parallel to AB. Okay, now why? because E and F are both the midpoints, they divide those lines in half. So we have CE, the ratio of CE to EA is equal to the ratio of CF to FB is equal to 1 to 1. And because the ratios are equal, the lines are parallel. Okay, and that's a nice converse result. Yeah, we're quite used to the fact that if we've got a pair of parallel lines, then it creates a pair of similar triangles. So if BC is parallel to DE, that implies that AB to BD is equal to AC to CE, but that's also reversible, which I won't prove here, but it'd be a good exercise to prove it. Okay, so EF is parallel to AB. Therefore, the perpendicular bisector of AB is also perpendicular to EF. So this angle here is a right angle. And by similar argument, the other perpendicular bisectors are also perpendicular to GF and EG. So this is a right angle, this is a right angle, and this is a right angle. So put it into the chat. How could we conceive of the point D? On the one hand, we know it's the circumcenter of ABC, but what other special property can we see of the point D? So what can we conclude? So put it into the chat. But what I hope that you're writing is that D lies on this line, which is the altitude drawn on EF. This line, which is the altitude drawn on GF, and this line, which is the altitude drawn on EG. So therefore, D is the intersection of the altitudes, of the three altitudes of the triangle EFG. So at the moment, what theorem have we proved? So at the moment, we've proved that the three altitudes of the triangle EFG meet at a point. Okay, so the altitudes of triangle EFG meet at a point. Have we proved, and vote in the chat yes or no, using this argument, that if I was to draw any triangle whatsoever, that the three altitudes would meet at a point? So vote yes if you think that I've essentially proved that the three altitudes of any triangle meet at a point, and no if you think that I've only proved the theorem in a special case. So at first glance, it looks like I've only proved the theorem for triangles which are made of the three midpoints of some bigger triangle. And maybe that doesn't cover every triangle. But is there anything special about, or is there any special relationship between this triangle EFG and the triangle ABC? Well, EF is parallel to AB. Okay, so these two angles are equal. But GF is parallel to AB, so that angle down here, this one, corresponds with this angle. And by a similar argument, this angle corresponds with this angle and is alternate to this angle. And by another similar argument, this angle corresponds to this angle, is alternate to this angle. So E, F, and G are similar. Okay, but E, F, and G are similar. Therefore, the altitudes of A, B, and C also meet at a point. Okay, and why? Okay, because ABC is just a scaled up version of EFG. But ABC is a general triangle, so we have as a theorem, that the altitudes of any triangle intersect in a point. Okay, I'm going to stop sharing here, and I'm going to go back to sharing my GeoGebra. And what I'm going to do is I'm going to get the orthocenter now of the big triangle. So I'm going to draw a perpendicular line. Okay, so I'm going to select the line A, B, and I'm going to go, oops. So I'm going to select the point C. A, yeah, C and AB. Okay. And now I'm going to select the point B and this line. So that's that altitude. And then I'm going to select the point A and this line. And that's that altitude. Okay. And so the orthocenter of the big triangle is this point here. Ah, and that's convenient. That's come out as H. Okay, and let's just move this around. And we see however we move the points around, the orthocenter H is always inside the, well, is always a single point. Again, it can sometimes be outside of the triangle. And you can convince yourself again that the edge case is when we've got a right angle triangle, and it's outside when it's a when there's an obtuse angle. Right, this is getting a little bit cluttered, this diagram, so I'm just going to hide. No, I'm just going to just color some things so they're different. So I'm just going to color the 3 altitudes red, and the 3 perpendicular bisectors I'll keep black. Okay, what other things do we know like meet in a common point? We also know that the medians meet in a common point, so I'm just going to draw the 3 medians. Okay, so the 3 medians, so that's C through G, and I'll just do the medians a different color, so that's going to be green, and I'm going to do the segment AF, and I'm also going to color that segment green. And then the 3rd median is through B and the opposite midpoint, which is E, and I'm also going to color that one green. Okay, and those 3 points meet in a point. That's come out as I, which I don't particularly like, because I is normally the in-center. So I'm just going to rename some of these points. So I'm going to rename this point EU. Oops, lost my window, sorry. I'm going to rename this point F, V, and I'm going to rename this point V, W, and I'm going to rename the circumcenter, which is currently D. I'm going to rename that the name that is normally given to the circumcenter, which is O. And I'm going to rename the points where the medians meet, which is the centroid. And I'm going to rename this point G. Okay, and I'm just going to convince myself that as I move around, whatever happens, O, H, and G, the 3 centroids, sorry, the 3 altitudes, which are the 3 black lines. A minute, this. Oops. A minute, I'm just. Oh yeah. So the black, the 3 perpendicular. I've just colored one of the lines wrong. Ah, yeah, this one. Oops. This line is a perpendicular bisector, and this line here is an altitude. So the 3 altitudes, which are the 3 red lines, always go through point H, which might be inside or outside the triangle. The 3 perpendicular bisectors, which are the 3 black lines, all go through O, and the 3 medians all go through or go through G. Does anybody notice anything, and this is a sort of geometrical pattern that you would never think of as being true if you never drew it. But does anybody notice anything special about the points O, G, and H? So O is the circumcenter, G is the median, H is the orthocenter. Anyone notice anything special about those 3 points? Yeah. And so Kieran said they are collinear. Okay, so let's just check if that's true. So I'm going to draw a line through O and H. And I'm just going to color this line. Let's do a very special color. Let's do it orange. So this orange line, I think, goes through O, G, and H. Now, as I move the points around, do O, G, and H always remain on that straight line? Do you know what? I think they do. Okay, now I don't think anyone would ever, without sort of just playing around with this diagram, have ever thought that. So what I'm going to do now is I'm going to take a snip. And I'm going to go into my OneNote. And we're going to do a proper piece of classical geometry now. And I'm going to claim the theorem I'm going to claim that the circumcenter the orthocenter, so that's the circumcenter is O, the orthocenter, that's H, and the centroid, that's G, are all lie on a straight line. And this straight line has got a name, and it's named after the mathematician who first proved this result. He's a very famous mathematician. It's called the Euler line. Okay, now, clever chap is Euler, but just think of all the geometry that's gone before, even to show that these points meet. Let's try and prove this result. So, does anyone have any suggestions about a proof? Now, what I'm going to do is I'm just going to zoom in on the centroid, okay, because we've got a very cluttered diagram at the moment. Okay, but does anybody remember from the sheet, the Euclidean geometry sheet 1, anything special about the position of the centroid on these 3 medians? So I've got A, B, C, U, V, W, and I've got G. Does anyone remember any property that connects C, G, and W? So if I look at the length CG to GW, oh, sorry, you're meant to be able to see my OneNote, sorry. Oh, thank you for letting me know that I wasn't sharing. This would be horrible without sharing. Can people now see my OneNote? Yes. Okay. Thank you. Oh, yes. I can feel your gratitude, because yeah, I was worried. This is why I was so worried at the start of the meeting when I couldn't share my screen, because it was, you know, this would be a very difficult session to do just by describing things. So, just to clarify what we should be able to see here. So we've got this diagram on the left, which shows the centroid, which is G. Okay, which I've just isolated in this diagram here, which is where the three medians meet. Okay, I've got the circumcenter O, which is where the three perpendicular bisectors meet. And then I've got the orthocenter, H, which is where the three altitudes meet. Okay, so three different pictures all in one diagram. So the green lines are the medians. The red lines intersect at the point H here, which is the orthocenter. And the black lines meet in the at the circumcenter, which is O. And what we're trying to prove is this result, which looks like it's the case, that O, G, and H all lie on a straight line. And this straight line we're going to call the Euler line. Is everybody, it's a bit difficult to sort of, I just want to check that everyone's happy with what I've done so far. If people are happy, can people put a thumbs up? Okay, good. Now, from the Euclidean geometry sheet, does anybody remember a relationship between the medians, the way the medians meet? Does anyone remember the relationship between this length, C to G, and this length, G to W? Okay. It turns out to be the case that the ratio of the two lengths is always 1 to 2. Okay, so CG is length 2, GW is length 1. Okay, with this in mind, can anyone tell me a relationship between UVW, this medial triangle UVW, and the big triangle ABC? So let us consider triangles. Triangles ABC and VUW. Now, we saw earlier that they're similar. But here we can do better. Okay, so if two triangles are similar, that means that one is just an enlargement of the other. can anyone see an enlargement that will take UVW, so this inner triangle, to the outer triangle ABC? So what enlargement takes UVW to ABC? Well, let's consider this point W. To get it to C, we want it to go past G and then out the other side twice as far. This point U, to get it to B, we want it to go past G and out the other side twice as far. And this point V, we want it to go past G and over to A twice as far. So what enlargement takes this inner triangle, the UVW, to the outer triangle ABC? How would you describe that enlargement? So to get from W to C, okay, we enlarge with center of enlargement G by a scale factor of -2. So the negative is because we're going to the other side of G. The scale factor of 2 makes sense because the larger triangle ABC is twice as big as the triangle UVW. Okay, how does this help? So what we know is that if we take this triangle UVW, so if we enlarge UVW by a scale factor of -2, we get triangle ABC. But let's remember something earlier on about this circumcenter O. This circumcenter O was had a slightly schizophrenic nature. So the point O which is the circumcenter of ABC, what did we see in the first theorem that we proved at the beginning? We saw that the circumcenter of ABC was the place where the altitudes of this medial triangle EFG meet. So what we know is that the point O, which is the circumcenter of ABC, is the orthocenter of UVW. But what we know is that if we do an enlargement of UVW by scale factor -2, we just get ABC. And that enlargement must take orthocenter to orthocenter. So the enlargement by a scale factor of -2, and center G takes the orthocenter, which is O of UVW, to the orthocenter of ABC, and that's H. So what we know is that if we've got the points O, G, and H, to get from O to H, we need to go past G and out the other side and go twice as long. So we know that, so we've not only proved that O, G, and H are collinear, we've also proved that they're also in the ratio 1:2. So therefore, O, G, and H are collinear, and OG to GH is equal to 1:2. Okay. And so if you stare at it long enough, and I'm not claiming that this is, you know, that this happens sort of overnight, but we can see that this middle triangle, this UVW, we turn it into the big triangle by flipping it about a center which is G and stretching it by a factor of 2. And if we do that, that must take the orthocenter of this inner triangle, which is O, to the orthocenter of the outer triangle, which is H. Okay, and so this result due to Euler, that those 3 points lie on a line, is sort of one of the highlights of Euclidean geometry. And I just thought I'd share that with you today. I appreciate that's a significant chunk of geometry. Okay, any questions about that before we move on? Something I would like to sort of advertise to you, if you've never seen this before, is my favorite go-to place if you want a little bit of a game on Euclidean geometry. Okay, and it's super addictive. Okay, but you can get it on the iPhone, and it's an app called Euclidean. I'll put that into the chat. Okay, and it's a game where, so there, no, you won't be able to see that, but it's called the Euclidean game. And basically, you've got lots of different levels, and you start with just a ruler and a compass, and you need to construct things, and you get bonus points for constructing them in the fewest number of ruler and compass sort of construction lines that you can. Okay, I'm just going to dig out a question. In the meantime, if you've got any questions, put it into the chat. If you're happy and you're ready to move on, put a thumbs up into the chat. Yeah. Sorry. Lottie, you shouldn't be in your roller skates upstairs.
Upstairs. You just tell me how to make downstairs. Can I take them off? But I'm not downstairs. How? How would I do it?
Lottie, you shouldn't be in your roller skates upstairs.
I'll take them once you told me. And I don't know how to do it.
Okay, Lottie, I'll put your roller skates off. Wait a second.
How do you pull them off? I mean, once you told me, right after.
A minute, Lottie, wait 1 second.
Ugh, fine, I'll wait 200 million years.
So I'm just trying to find the construction which I want. Okay, okay, I'm gonna. Okay, I'm going to go back to GeoGebra, and I'm going to actually no, I'm going to go back to my OneNote. I'm going to set a problem. Okay, and we're going to build up to a really nice bit of classical geometry. So what I'm going to do is I'm going to draw a triangle. And I'm going to draw the in circle of that triangle. So we've got A, B, and C. And we've got the in radius R. And we've got these 3 points, which I will call E, F, and G. Okay. And the first thing I'm going to do is some little bit less intense geometry than before, but we will build it up. First question. Find an expression for the lengths AG, BG, sorry, I'll say BF and CE in terms of the lengths of the triangle. A, B, and C. So in normal way, we would define the length BC, so the side length opposite A, as little a, the side length opposite B as little b, and the side length opposite C as little c. So any offers of how to find an expression for the side length AG in terms of A, B, and C. And then the next part of this question will be part B, find an expression for the area of the triangle in terms of A, B, C and the in radius R. Okay, so let's do part A first together. We've got 24 minutes. Yeah, we can get to another highlight of classical geometry in 24 minutes. Okay, so can anyone tell me the relationship between AG that I've just highlighted and AE over here? So we're looking at part A. So what is the relationship between AE and EG? So AE and EG, sorry, and AE and AG, I claim are equal because they are tangents to a circle from the same point. Okay, and this is the sort of thing which you should be able to prove. Okay, well, we know that tangents and radiuses are perpendicular. We know that the incenter lies on the angle bisector. So we can see that these two triangles, AEI and AGI, are congruent. So AE equals EG. Similarly, I can say that BG is equal to BF. Because they're also tangents from the same point. And finally, CE and CF are equal because they're tangents to this, from the same point. Okay, so CE is equal to CF, and they are tangents from C. Okay, so next observation is I know that if I was to add the green length, the yellow length, and the blue length, okay, that if I was to add two lots of them, I would get the whole of the perimeter of the triangle. Okay, so if I would just add one of each, one green, one yellow, and one blue, that would be half of the perimeter of the triangle. That would be A plus B plus C all over 2. Okay, does that take us anything, does that get us anywhere closer to finding this green length AG? Well, we want the green length on its own. But do I have a nice expression for what I get if I would add the yellow and the blue? Any offers in the chat for what happens if I just add the yellow and the blue? A lot of people are. So the yellow and the blue together just make this side over here, which is opposite A. So the yellow and the blue together is equal to A. So if I just subtract the two from one another, I know that this green length, which is AG, is equal to A plus B plus C over 2 minus A, which is B plus C minus A over 2. So this is B plus C minus A over 2. The yellow length is A plus C minus B over 2. And the green and the blue length is A plus B minus C over 2. So this is a nice, well, not nice, but this is an interesting way of splitting up, of getting, we could easily find the position of the 3 points of intersection of the incircle from the side length. So we know where the incircles meet the meet the side lengths. So that's a nice bit of geometry. What we're going to look at now, and I think I will show it in GeoGebra, is a new bit of geometry. And something which sorry, I need to share my GeoGebra. Okay, so what I'm drawing here is a triangle A, B, and C. And actually, I'll draw the line AC as well. When we looked at the in-circle, we did the angle bisector of the interior angles. What I'm going to look at now is I'm going to look at the angle bisector of the exterior angles. I'm just going to get a point. I'm just going to get a point on these lines. And I'm going to get a angle bisector of DBC and ECB. And they meet at a point. Okay, and I'm just going to drop the I'm just going to get that point where they meet, call it F, and I'm going to drop a couple of perpendiculars from F to these lines. Okay, and I'm going to take a snip of this, ready to move into my OneNote. And while I do that, try and think of a nice geometric property which is satisfied by F. Oh, actually, it's a bit difficult. I'd like that geometric property to be shown. So try and think why this point F has the following geometric property. So what I'm going to do is I'm going to draw a circle with center F. I'm going to draw a circle with center F going through the points G and H, so where it meets those two lines. I'm now going to take a snip, and in the meantime try and think why F has this nice property of being on this circle. This will be reminiscent of the Euclidean problem sheet. But let's put it as a theorem. Okay, so my problem is the angle bisector of the exterior angles of a triangle at B and C meet at F. And the problem is prove that a circle with center F touches the lines AB, AC, and BC. Okay, so it's a little bit like an in-circle in that it touches the three lines of the triangle, but it touches externally. And so this circle has got a name. This circle is called the X circle. Okay, so my claim is that F touches these three lines. Okay, so let's have a little bit of a proof. Okay, and I'll do it all from first principles. Okay, as we have an angle bisector, these two angles are equal. Okay, and these two angles are equal. Now, there's some point on the line BC that I can draw that will be perpendicular to BC and pass from F. So I'm just going to drop a perpendicular here. And what do I know? Well, the first thing I know is that I've got a right angle triangle here and here. And because I've got an angle bisector, these two angles are the same. So the triangles BGF, and I'll call this point K, and triangle BKF are congruent. Okay, because they share two angles and they share the side SS. Okay, because the angle BGF equals angle BKF equals 90 degrees, and because angle GBF equals angle FBK, because we've got an angle bisector, and they share BF. And so because those lines are congruent, because those triangles are congruent, GF is equal to KF. Yes, someone's raised a hand. Oh, you're still seeing the GeoGebra, sorry. Let me share my OneNote now. So sorry. Okay, so I've taken the snip. Thank you so much. So I've taken the snip from GeoGebra, and I'm trying to show that this point F, where the two angle bisectors, so this line here, BF, is an angle bisector, so these two angles are equal. And this line here, CF, is an angle bisector, so these two angles are equal. And I'm trying to prove in this theorem what I've shown in the GeoGebra, that the circle with center F touches these three lines. So it touches the triangle line AC externally, AB externally, and BC internally. And the way that I did this was that I dropped a perpendicular from F to the line BC. And then I argued that these two triangles, BGF and BKF, so these two right angle triangles, they were congruent because they shared a hypotenuse and they also shared an angle. And if they are congruent, then these two lengths, GF and GK, are equal. But what I can also do is I can also get a second pair of congruent triangles. Okay, I can get the pair of congruent triangles KFC, Kentucky Fried Chicken, which is congruent with HFC. And again, they're congruent for the same reason, that they share the hypotenuse CF, and because there's an angle bisector, these two angles are equal. So similarly, triangle KFC is congruent to triangle HFC, because FC equals FC, angle CHF equals angle CKF equals 90 degrees, and angle KCF is equal to angle HCF because we've got an angle bisector. Okay, and if those two angles, if those two triangles are congruent, then KF equals HF. So these two lengths are the same. And now, if we just get rid of all the construction lines, the lengths that we've shown are the same, are GF, KF, and HF. So the points G, K, and H lie on a circle. So points G, K, and H lie on a circle with center F. But now we've also got something interesting. We know that GF is equal to HF. So if I was to draw the line AF, I have a pair of congruent triangles, AHF and AGF. Okay, so therefore, triangle AGF is congruent to AHF, which means that F lies on the angle bisector. Okay, so if I just go back to my GeoGebra, let's just see if the little bit of geometry which I think is true is true. Okay, so what I think is true is that if I draw the angle bisector GAH, that goes through F, and indeed it does. And if I just draw my incircle, okay, then okay, if I just draw my incircle, then I can show that I and F lie on the same line. So let's take a snip, stop my share. Let's go back to my OneNote. Okay, so let's try and think of, let's see if we can see, and let's see if we can get any facts. Let's see if we can get any facts straight from the get-go. So earlier, we found these lengths. We found B plus CO minus A, we found A plus C minus B, and we found this blue length up here. Let's think about what happens when we start marking them on this diagram here. So we know that So we know we've got this length here is AG. We know this length BG is equal to this length here. But we also know that that length is equal to minute. No. No, we need to be a little bit careful. Okay, so I know that the length BG is the same as the length to the point where we touch the big circle. And I know that the length HC is the same as the length to where we touch the big circle on the other side. So what I know is that what I've called yellow plus green here is equal to the whole side CB, so is equal to A. But what I also know is I also know that B plus yellow plus yellow is this whole length to where we touch the big circle is the same as this length, which is C plus green. So these two are equal to one another. So what I can say is that yellow minus green is equal to C minus B. Okay, and if I add the two together, I get two lots of yellow is equal to A plus C minus B. So yellow is A plus C minus B over 2. Green is A plus B minus C over 2. And what it turns out is I can show that this distance AG is A plus B plus C all over 2. Okay. So what we can also show is we can get an expression for this outside radius R and this inside radius R via similar triangles. Okay, so we get that R over A plus B minus C over 2 is equal to big R over A plus B plus C. So we know that R over R is A plus B minus A plus B plus C over A plus B minus C. Okay. What I wanted to show, but I think I'm sort of running out of time, running out of steam a little bit, but I'll set it as a extension problem, is we're close now to being able to find an expression for the in radius in terms of A, B, and C. But what we can also find in terms of the in radius, and this is quite straightforward to do, is we can also find an expression for the area of the triangle in terms of A, B, C, and R. Okay, and I'll just do that very quickly. So if I've got any triangle and I draw an in circle, I can draw the in radius and I can find the area of these three triangles, the triangles which sit on each of the three sides. So this green triangle is half base times height, and the base is little c. So the green triangle is half c, and the height is r. The yellow triangle is half base times height, but the base is this length, which is b. So the yellow triangle is half br, and the blue triangle is area half a r. So the area of the whole triangle is half a plus b plus c r. So the area is the semi-perimeter of the triangle times the in radius. Okay. If we were to continue doing this geometry of finding similar triangles, okay, so showing that this triangle here is similar to this big triangle here, and showing that this triangle here is similar to this triangle here, and using these lengths that we found earlier for the lengths of the different sections of the triangle, okay, if you were to continue this argument, you could prove a wonderful theorem from classical geometry, which is called Heron's theorem, which is that the area of a triangle is given by the semi-perimeter multiplied by the semi-perimeter minus a, multiplied by the semi-perimeter minus b, multiplied by the semi-perimeter minus c, all square rooted. And I should just mention that these brackets, s minus a, s minus b, s minus c, are exactly these lengths here. So this length here is s minus a, this length here is s minus b, and this length here is s minus c. And I've broken the back of the proof here, okay, and the argument is to find similar triangles in the diagram here. Okay, and the similar triangles are AJI, which is similar to AGF, and BJI, which is similar to BGF. And if you use those two similarities and use the lengths that were found previously, that this length is S minus A, this length is S minus B, and this length is S minus C, this is R, and this is the in radius, you'll get Heron's formula. Okay, so for example, the similarity of these two triangles gives me that R over S minus A is equal to big R over S, and the similarity of the two smaller triangles gives me that R over S minus B is equal to S minus C over capital R. And if you eliminate capital R, so you write R equals RS over S minus A, you get that R is equal to S minus C, S minus B, R over S minus B, S minus A over RS. And now you can see where we're going. So now we get R squared S is equal to S minus A, S minus B, S minus C. And if we add another S, we get an expression here, which is exactly the expression for the area squared. So that would give me Heron's formula. Anyway, I'm going to stop the share there. Oh, a minute, there's a hand up. Oh no, did I not? Sorry, I think I missed the... Oh dear, that would have been impossible to follow, sorry. Oh no, so I'm so sorry, everybody. I will just redo this last bit. This is going to need a little bit of post-editing. So basically, my key diagram was this diagram, which shows the X circle and the in circle. I then used the lengths that I found earlier for the sections of the triangle between the corners and where the where it touches the in circle, which turn out to be the semi-perimeter minus A here and here, the semi-perimeter minus C here and here, the semi-perimeter minus B here and here, and the semi-perimeter minus C here. So this whole length here is the semi-perimeter. Then what I establish is two sets of similar triangles, this similar triangle and this similar triangle, which gives me R over S minus A is equal to capital R over S. And then another pair of similar triangles here and here gives me R over S minus B is equal to S minus C over R. R is the X radius. If I eliminate the X radius between these two expressions, I get that R is equal to S minus A, S minus B, S minus C over RS. So I get the expression r squared s is equal to s minus a, s minus b, s minus c. But what I established earlier on as well is that I can get the area in terms of the in radius by breaking the triangle up into 3 little triangles, each with height being the in radius. And these 3 triangles have got area half AR, half BR, and half CR. So the area of the triangle is half A plus B plus CR, which is the same as A times the semi-perimeter. So the area is SR. And so if I multiply by S in this expression, the left-hand side becomes the area squared. And so I get this lovely famous formula, okay, of a mathematician called Heron, which gives me the area of a triangle expressible as a formula of the side lengths. So a few technical difficulties to begin with, needing to share the screen, a few difficulties going between different applications, okay, but hopefully it was worth it because we also did 2 real high points of classical Greek geometry. So we showed this lovely result of Euler, that these angle centers, which we looked at on the problem sheet Euclidean 1, that these triangle centers lie on a straight line. And we did that through getting a transformation that took the inner triangle that you get by joining the midpoints to the outer triangle, and noticing this lovely duality that the circumcenter of the big triangle is where the altitudes of the inner triangle meet. So when you do this flipping and stretching to turn the small triangle in the big triangle, the where the circumcenter of the original triangle was maps to the circumcenter of the larger triangle. Then we did some more classical geometry. So we found the lengths of the sections of the triangle, the sides of a triangle that take me to the point of contact with the in-center. And so we got these lengths. Then we showed that we can get an X circle by doing very similar geometry with congruent triangles to how we got the in-center. Then we spotted a whole bag of similar triangles relating triangles that involve the in-center to triangles which involve the X-center. That bit would have been incomprehensible when I wasn't sharing my screen. And then those similar triangles allowed me to find an expression for the in-center, just in terms of the side lengths. And then because the in-center is related to the area, I found the area in terms of the side lengths. So that is a little whistle-stop tour of 2 high points of classical geometry. Okay, so I will stop what I have to say there and just check that if anyone's got any questions, either about this or about the sheet, before saying goodbye to people. So any questions? Super. Okay, if not, I hope you all have a lovely Christmas. Oh, wait a minute, there's a thing in the chat. What's the next assignment about? So the next assignment is more Euclidean geometry. Okay, but this time we're going to strip things right to right back to the axioms. So it's going to be an introduction to axiomatic systems, which is of massive historical importance, because this is why sort of Euclidean geometry was sort of deemed important in the first place. So we're going to sort of think about how to set up Euclidean geometry if you don't take anything for granted. So how do you actually prove these really basic results that you think that you've always known, like the angles in a triangle add up to 180 degrees? How do you show that alternate angles are equal? And early on, we will hit a sort of philosophical problem, which is, well, if you don't assume anything, then every time you prove a result, you have to prove a result from other things. Well, how do you prove those things that you prove it from? So to avoid that infinite regress, you have to sort of set a foundation. You just have to say, look, this set of results, we will just assume are true, and then we will prove everything carefully from that base. And that whole system of thought is what's called an axiomatic system, and we will reapproach Euclidean geometry from that basis. So we will start by the most basic statements you can make about Euclidean geometry. So we'll start saying things like, the first axiom of Euclidean geometry is that if I draw 2 points, who knows what a point is, but if I draw 2 points, I can always draw a unique line that goes through those 2 points. And there'll be lots of unpicking of the logic of what is meant by sort of unique and stuff like that. Okay, any other questions? Super. Okay, well, I hope you've enjoyed this. I will share the I'll share the notes and maybe some references so you can look in more depth in your own time, both at the Euler line and Heron's formula, and I will see you again soon. Okay, bye-bye, everybody.